Annual checkup. After an annual checkup, you leave your physician's office where you weighed 683 newtons. You then get into an elevator that conveniently has a scale. Find the magnitude and direction of the elevator's acceleration if the scale reads in part A 725 newtons and in part B 595 newtons. So we have three situations. One, where the acceleration of the elevator is 0, the first situation, that is your true weight that you have measured also in the physician's office. And then situation 2, when the elevator is accelerating upward. Situation 3, when the elevator is accelerating downward. So first of all, if you are in an accelerating reference frame, note that that is a non-inertial reference frame. So let's start by making a simple observation that, so let's note that the elevator is a non-inertial reference frame. So in case 2 and case 3, when the elevator is accelerating, there will be a fictitious force appearing on the person. So therefore, as with any other non-inertial reference frame, in an accelerating elevator, if you're trying to read a scale inside the elevator, so that's an observer is in the non-inertial reference frame, a fictitious force, or we also call it ghost force, will appear on the person. Okay, so let's draw a free body diagram for the person to understand what is going on in each situation. So the person is modeled as a particle. There is the weight of the person pointing down, mg, and the normal force from the scale pointing up. So this is the first situation where we read the correct true weight of the person. Now in situation 2, we still have the same forces, the weight of the person, mg. And in this situation, since the elevator is accelerating upward, a fictitious force will appear downward. A fictitious force which has magnitude mass times the acceleration of the elevator will be pointing downward, and the normal force from the scale will have a new value, ns prime, that will correspond to the reading in this situation. And in the third case, we have the weight of the person again pointing down, mg. The scale will have a reading, the normal force, double prime, because in this situation the elevator is accelerating downward, the fictitious force will appear upward. So fictitious force, that's going to be equal to mass times acceleration in the third situation, will be pointing upward. Okay, so let's analyze these situations. So first of all, the true weight situation, we have case 1. In case 1, when the acceleration is 0, the elevator is an inertial reference frame. So all the forces are real. The normal force on the scale will be equal to the magnitude of the gravitational force, which gives us a reading of the true weight of the person. And the scale reading will be 683 newtons in this case, which means that the mass of the person will be equal to 683 newtons divided by the gravitational acceleration 9.8 meters per second square, and the answer will be in kilograms. So let's move on to part A. In part A, the reading is 725 newtons, so it is more than the true weight, because now the normal force is basically balancing the fictitious force and the weight. So that will correspond to case 2, where we will have the normal force from the scale will be balancing the weight of the person and the fictitious force m times acceleration in the second situation. So this will be equal to 725 newtons. That means mass times the acceleration in second case will be equal to 725 minus 683, which is 42 newtons. So this will give me an acceleration in the second case to be equal to 42 newtons divided by the mass m. So the acceleration in the second case, therefore, will be equal to 42 newtons times 9.8 over 683, because the mass was 683 divided by 9.8, and that will be equal to 0.603 meters per second square, pointing upward. This will be the acceleration of the elevator, the magnitude and direction. In part B, we have the third case, case number 3, where the normal force from the scale plus the fictitious force, mass times acceleration, will be equal to the weight of the object mg. So the acceleration in the third case will be equal to mg minus the normal force ns double prime divided by m. So this will be 683, the true weight, minus the normal force 595, the reading on the scale given in part B, and this is divided by 683 multiplied by 9.8. 683 over 9.8 is the mass. So this gives me, for the acceleration in this case, 88 times 9.8 divided by 683, which is equal to 1.26 meters per second square, pointing in the downward direction. Okay, so to summarize, we have three situations where we're trying to measure the weight of this person. The inertial reference frame is a non-accelerating reference frame where all the forces are real. The normal force from the scale balances the weight of the person. This is what is measured in the physician's office or in a non-accelerating elevator. In the second case, the elevator is accelerating upward, fictitious force points downward, so that the reading on the scale is more than the true weight. In the third case, the acceleration is downward, fictitious force is upward, so that the reading in the third case will be less than the true weight. Okay, so in all of these situations, we write the net force on the y-axis equal to 0 because we have an equilibrium situation. So this is my y-axis. And the true weight, from the true weight 683 newtons, I can get the mass of the person, 683 divided by gravitational acceleration 9.8. Then I substitute for m this quantity. For case 2, the scale reading is basically reading the fictitious force ma2 plus mg. In the third case, it is reading mg minus ma3. So we substitute for m this value, and the reading on the scale 725 newtons for the first case, second case, and 595 for the third case. So that is the normal force provided by the scale on the person. So substituting these values, we find that in the second case, the acceleration is upward with a magnitude 0.603 meters per second square. In the third case, it's downward with a magnitude of 1.26 meters per second square. So basically, this is downward, this is upward, and the acceleration is different for the two different cases.